Last time we started looking at rational expressions. So the last section of material is kind of like day one of looking at fractions back in section 1.3. The first thing we looked at was reducing and simplifying, making things look nice and neat with multiplication and division, right? That's what we did in the last section as well. We just did it with polynomials, okay, top and bottom. So this section is going to involve addition and subtraction, which was the equivalent of what we did in 1.4 with fractions. And the tricky thing with addition and subtraction that you don't have to worry about at all with multiplication and division is that what do you have to have when you add and subtract fractions? You have to have a common denominator, right? So that makes it harder. This section's harder because common denominators come into play, just like section 1.4, adding and subtracting fractions, is harder than 1.3, which was multiplication and division and reducing of fractions. So, last time we simply looked at rational expressions, including multiplying and dividing, and found that all the process we use for fractions with variables work the same way as fractions without variables. The same will be true today as we add and subtract. My guess is that the homework might take you a little longer because you have this extra sort of layer of groundwork in it to get those common denominators than it might have before. Okay. So kind of some starter work is we're going to take a look at what we do when we find common denominators. And in particular, we really do want least common denominators here. We want the pieces that are there to be there only once. When we were working with fractions, sometimes, common denominators are good enough. If they have something, that makes them a little bit smaller, that would be nice, but it's not super crucial. Here it becomes more necessary. So this one asks us to find the least common denominator. So this denominator is x plus 10 and this one's x minus 10. I know they both have an x and they both have a 10. But they have to have the entire pieces in common as a whole factor, not individual terms. So there aren't any pieces here that they have in common in terms of factors. One is a factor x plus 10, the other is a factor x minus 10. You can think of it like this, like if one was on top of the other one, you couldn't reduce them, right? If you can't reduce them, then they don't have any factors in common. So when that's the case, the least common denominator, I'll identify it that way in fact, would simply be what happens when we multiply them together. Here's the good news. You don't have to distribute it out. We're not doing that, right? Because when we get back into the actual problems we're going to use least common denominators for, what we're going to be doing is combining fractions together and reducing and seeing things factor out in the end to simplify. If I multiply these out and then I have to refactor them at the end, that's very counterproductive. So your least common denominator is done at that point. That's good news, right? It is. You don't have to distribute or multiply it back out. Yeah, okay, we'll do it in just a second. But what we would do, Kaylee, is that we would actually have to multiply each of them by that other piece. So I'll show you what it is and I'm erasing it, so don't write it down, but I'll answer your question. You'd be multiplying this by x minus 10 and this one by x minus 10. And you'd be multiplying this one by x plus 10 and this one by x plus 10. That's what you would do to then combine them with addition or subtraction. Okay, we'll get to the next problems. We're not asked to do that on this problem. Kaylee was just asking another question. Kaylee was asking if I were adding or subtracting that, what would I do next? Kenny?
Does it matter if would this be the same thing if it was x minus 10 and x minus 10?
No. In fact, we are going to have that happen on the next problem, so let me show you. Okay, so on number 2, do you see how the denominators match already? They're both 5x, like they would be if you said they were both x minus 10s. If the denominators are already the same, the least common denominator is the one that they already have, the same, 5x. So our goal with least common denominators is to get the denominators to match. If the denominators already match, we're sort of one step ahead in the game. And so they do here, right? I have 5x as the denominator for both of them, so I would combine the numerators together, written over the same common denominator, and then I would actually simplify. So what is 8 plus 6? 14. So I have 14 over 5x. Now at the end of the problem, I still need to know, do I reduce? 14, 5, do they simplify? No. They could have. I mean, if I had 15 and 5, right, or 14 and 4 or something, but these don't. So we're done. Okay, so the only purpose of finding least common denominators is so that we have common denominators to be able to combine them with addition or subtraction. On this one, they were already like that. And number 3 is as well, much like the question you asked about number 1, Kenny. They already match. They say y minus 5. Well, if they already match and they say y minus 5, they already share a common denominator, and I can simply join the numerators with whatever operation, in this case subtraction, that was between them. So y minus 2, because the first piece was y, the second piece was 2, and they're joined with subtraction, over y minus 5. Don't get carried away and start canceling things, right? All the things you just did in section 2 point, whatever we were in before, 2.6 apply. All that still happens. They don't have factors in common. You can't simplify this any further because none of their factors match. Okay, so we have a couple more that are going to feel much like this, where pieces already match. Number 4, the denominators match, right? Yeah, they do. So since the denominators match, we're going to combine them with their same operation. In this case, it's subtraction between them. So I have 9x. I even have multiple variables this time, minus 3y. This negative has to apply to each piece. So it's minus x, and it's minus a negative 10, which makes it positive 10y. Remember, that's why we were talking about integers back in early section 1.2. Yes,
So
Haley.
you just mushed the two top ones together.
Yep.
And
With
that's why there's like a minus and an X.
exactly, and that's actually what I did over here on number 3 as well. It's just that they were simpler, so it didn't feel quite as quite as complicated. Yeah, there were simpler fractions, simpler numerators. But yeah, and we don't get to stop here on this one, right? There's still a mess on top that can be combined and simplified, cleaned up, and so forth, so we will. So we have 9x, and the common term for that is the minus x. That gives me 8x. And then we have negative 3y and positive 10y, which gives me, yep, it's positive, isn't it? Yeah, positive 7y. My denominator is 2x. The coefficients don't have anything in common, right? They're not all they're not all evens, or they're not all divisible by 3 or something like that. Same thing's true for the variables. I have x's in some pieces, y's in some pieces. I don't have common variables to reduce out. So I'm stopped at this point. There's no more simplifying. Bailey.
So why can't you do the 2x and the 8x? Because then you could cancel the x and the 2.
Yeah, so in order to do that, I would have to separate this back out into individual fractions. And the whole goal was to have one fraction. So could I rewrite this as 4 plus 7y over 2x? I mean, yes, I could, but that wasn't the goal. The goal was to have one single fraction when I was done. Okay, so you present a good question in the general idea of, well, what if it reduces with one piece and it doesn't with the other? Then it doesn't simplify for the whole thing. Okay, so let's say for a moment, let me just make something up a little bit different. Let's say it said 8x plus 6y equals 2, or I'm sorry, over 2x. The reason that I'm able to cancel a 2 out of all the terms, right, is because what I'm actually able to do is factor a 2 out. And they actually cancel as a factor. We just kind of shortcut that step a lot of the time and we say, hey, look, they're all even. I can divide them all by 2. But the reason that that works is because I can factor a 2 out of all of them. And in our problem right here, we can't do that. Okay? All right, any other questions about number, what we were on, 4, number 4. Okay, number 5 also has common denominators, yeah? Okay, so same things as we did before. Now I have z and I have plus 3 on top. And I have the same denominator, z squared plus 7y z plus 12. Am I done? No. How is this one different than the other ones? Yeah, the denominator could be factored on this one, right? The denominator could be factored. So if you need to do AC, do that. If you want to do trial and error, do that. And I'm going to pause for a second. And once you're paused for a second, have everybody have a chance to try it. I'm going to ask you what you got for your factors. So don't blurt anything out yet. Let everybody have a chance to do it. Okay, we're getting close to the writing being done, so I think you guys have factored at this point, most of you. What did you get for the factors of the denominator?
Z plus 3, Z plus 4.
Good. It is z plus 3, z plus 4. And what do you see?
Z plus 3 can cancel out.
Yes.
Z plus 4.
So, Maxwell, tell me what I'm left with?
Z plus 4. 1 over 1.
Under 1. Yeah, it's okay. The z plus 4, that's why I was making sure I heard what you said. The z plus 4 is what we're left with, but it's still in the denominator with a 1 in the numerator. Okay? Okay, so we're shifting gears when we flip the page. Kenny, you have a question or no?
What?
You have a question or are you stretching?
Oh, so we're gonna have to do AC method still?
Well, you know, at some point you might decide you like trial and error.
No, I really do like it, but it's starting to drive me crazy.
So,
Like last
it's
time
your
it
choice.
showed up twice in a problem, and I was like,
I know. It's your choice. I will tell you, I mean, eventually the AC method becomes like that, where you're like, seriously, is this going to take me this long every single time?
Yeah.
So the coefficients that we're dealing with are mostly coefficients of 1, which make the AC methods, or which make trial and error pretty nice. So if you take a look at the AC method and you have a coefficient of 1, you can almost shortcut your system. You know you're looking for something that multiplies to 12, right? And that adds to 7. And those are the numbers 3 and 4 at the end. That only works if your coefficient on the x squared is 1. But most of ours have been. They aren't always, but a lot of times they are. So you might be able to shortcut some of them if you think of it that way. Okay, so how's 6 different? The denominators don't match, but they're close, right? They both have a 3 in them. So what's missing? An A. One of them's missing an A. So if it's missing, we introduce them, right? And we say, hey, A, come along for the ride. Join 3. But if you join them on top, on the bottom, you have to join on top too. Yeah, you do. It's part of the deal. It's kind of like, you know, when you get married to somebody that already has kids, they sort of are package deal. It's a package deal here. Yeah. I mean, like I haven't married somebody with kids already, but I mean, it still is. It's a package deal. Okay, it's a package deal. You get it on bottom, you get it on top. Okay, now the denominators match 3a. How about those numerators? Well, they don't match, but I can combine them, right? 7 minus 2a. And you're done because there's nothing in common to all 3 pieces, all 3 of those terms. Okay? So they didn't have a common denominator, we got a common denominator, and then we combined them together. Now, number 7. They don't match, but they do have something in common as a factor, right? What factor do they have in common? An x. Because if you understand this, like really this is 7 times x, right? I mean, we never do that. We never write it out that way, but we should think of it that way. It is 7 times x and 6 times x. Now, we did that when we were looking at numbers, where we factored it down, and once they had the pieces that were in common, we sort of ignored them, and we said, hey, look, it already has an x in it. I can ignore it. 6 factors further, but nothing that's in common with 7. So I can actually take this 6 and I multiply it here. And I take this 7 and I multiply it here. You don't necessarily have to show my branches with the pieces down there, but that is exactly what we did before when we had numbers. So it works here too, if you'd like. So my denominator is now what?
42x.
42x. That's one of those multiplication facts that my 11-year-old still struggles with. 7 times 6. Man, she struggles with that one.
So we do keep the x. The x
Mm-hmm.
doesn't go.
The x doesn't go away. It's just already there. So we don't need to actually include it additionally. It's already there. Okay. We have 6 times negative 5. That is negative 30. And we have positive between. And then we have 1 times 7 is 7. So what's my numerator? Yep, negative 23 over 42x. And they don't have anything in common. 23 is prime, so we're stuck.
Yay.
Yay, nothing in common is always nice.
Why did you do the little branch things?
I just wanted to sort of do a connection back to how I had done it before when it was numbers involved. When we had done it before, like let's say that we had, I'm just going to make them up, but let's say we had negative 5 over 8 and we had 1 over 6. One of the things we did back then is we said we can break this down into 4 and 2 and like 2 and 3. And we said we can ignore the 2's that they have in common and the piece they don't have in common gets multiplied. And it's exactly the same thing with variables. We just don't usually write it out in quite the same way, but it can be written out in the same way, so I wanted to show you that. Okay, how about number 8? Okay, who said that? Was that you, Megan? Megan, say it loud.
You just multiply by 2.
Which one?
The 40.
Okay, so 4D, not 40 as 40, but 4D as 4D.
Yeah.
You said it right. It's just one of those ones that sounds the same.
Yeah.
In fact, on this one, I don't really need to multiply 1 by 8 and 1 by 4. That's overkill. If I simply multiply the 4 by 2, I get 8. So be careful. This would be one of those cases where, could you do it the other way? Like, could I multiply this one by 8 and this one by 4 and get a common denominator? Well, yes, I could. They'd match. It'd be okay, but then we'd have more reducing to do at the end because I overdid it, right? I did more than was really necessary. So 2's enough. So I have 9D minus 1 on top of the, well, they're all over 8D now. I'm going to move that actually because I feel like I'm running out of space already. And then this 2 will be distributed through, right?
Yeah.
Positive 4D minus 6. Okay, denominator still 8D. Combining like terms, I have, oops, that was supposed to be my highlighter. 9D and 4D, which is 13D. And then I have negative 1, and I have negative 6, which is negative 7, all over 8D. And that's as good as it gets right there. Those numbers are not at all reducible. Okay. So based on the ones we've done so far, you might look at number 9 and say, hey, they have an X in common. But they don't. How is number 9 different than 8 and 7 and 6? Yeah. This addition changes the game. It just does. It does not make it like the other ones were at all. If it helps you to think about it, you can think about it sort of in a grouping way, right? Those are factors, and they're grouped together because they've got addition, one of them at least, in between them. So it's a factor. It can't be separated into X and 1. Now, because they don't have anything in common, because they don't, it means their least common denominator is the product of them. Like I have to multiply them by each other. So I'll be multiplying X plus 1 on both of them, on the top and bottom of the first fraction, I mean, and X on the second one. So this is kind of like the very first problem that you asked me about, Kaylee, that I said, but we're not doing it on this one, right? I had to multiply both the denominators together to get that least common denominator. Now, again, there's no reason to multiply this out. Just leave it in factored form in the denominator, okay? Leaving things factored is preferable to multiplying them out, and it's less work. It's always nice when that happens, isn't it? The less work and the preferable option? Absolutely. Don't do more work than is necessary. Now, on this other piece here, we're going to distribute the 7 through to the x plus 1, or you could say the x plus 1 each gets multiplied by 7. So I have 7x plus 7. And then this piece is, of course, 6x, but it's negative. So negative 6x. What does that leave me with? X plus 7 on top, and then x times x plus 1 on bottom. And I'd like to tell you why that's preferable. It's preferable because I look at it and I absolutely know I can't cancel anything. Right? Yes, Kenny.
Where did you get your x plus 7? Where's the rest of it?
7x minus 6x. Yep.
Yeah.
Bailey?
Okay, so we made the 6 negative.
Yes.
So why didn't we make the x plus 1?
This right here had a negative sign in the middle.
Yeah.
So that's why the 6 is negative. But over here, there's no negative sign over here. Right? Like it actually told me that I'm supposed to be subtracting all of this from the first piece. So the second piece's numerator is negative, but the first piece's numerator did not have a negative sign on it. I'm not quite sure what else to say because there's a negative here and there's not in the other one.
Yeah.
That's why it's negative.
I just don't understand why it's down here.
Well, over here you can also think that this is actually means negative 6, right? That's another way to maybe think about it. So it's the negative 6 here that gets multiplied by the x, but here it's a positive 7 that gets multiplied by the x plus 1. Does that help? Okay. All right, so I would like for you guys to get started on this homework because you're going to have more of this need to find common denominators here than we have had any need for recently, finding common pieces. So let's go ahead and get started.